start inside the recruitment whisper network of semiconductor engineers, where compensation numbers are treated like classified leaks rather than job postings. Build a case through cause and effect chains linking export controls, talent scarcity, and strategic recruitment incentives. This is less about hiring engineers and more about importing embedded manufacturing intuition that cannot be reverse engineered quickly. Mood applied, cold and analytical, prioritizing mechanism over drama. There's a number floating around in semiconductor hiring circles that keeps getting repeated with slight variations. $600,000, sometimes $800,000, sometimes structured in bonuses spread over relocation, housing, and retention clauses. It's being tied to China's push to bring in foreign chip engineers. I want to be careful with how I treat that. Not because it's impossible, but because in this industry, numbers like this often behave more like signals than verified payroll data. Still, the direction of movement matters more than the exact figure. What matters is that Beijing is, reportedly, willing to pay a premium that sits in the same psychological bracket as Silicon Valley senior compensation. That alone is a shift. This video is not really about salaries. It's about what happens when a country decides that semiconductor capability is no longer something it can patiently develop internally at the pace of universities and domestic training pipelines. And the timing matters. Since the U.S. export controls expanded around advanced lithography tools and AI-relevant chips, especially the tightening waves in 2022 and 2023 targeting high-end GPU and EUV-adjacent ecosystems, the global chip industry has started splitting into layers that don't fully talk to each other anymore. Not cleanly, anyway. China didn't lose access to chips. It lost access to certain ways of making them. That distinction sounds academic until you realize that semiconductor manufacturing isn't just machines and designs. It's thousands of tacit decisions made on factory floors that never appear in documentation. That's where this recruitment push becomes interesting. If you assume this is just about brain drain, you miss the structure underneath it. The global chip ecosystem isn't short of engineers in the abstract. It's short of engineers who have actually debugged yield loss in a 7-nanometer fab under real production pressure, where every percentage point translates into billions over time. A trained EUV process engineer from a leading Taiwanese or Korean supply chain isn't just knowledge. They are compressed operational history, years of failure modes, material quirks, vendor inconsistencies, all internalized. And that kind of knowledge doesn't transfer cleanly through textbooks or even corporate training programs. It migrates slowly, usually through people. My read is simple here. If the compensation figures are even directionally accurate, this is less about filling vacancies and more about accelerating an industrial learning curve that sanctions attempted to stretch. But there's a tension in that strategy, because talent mobility in semiconductors is not neutral. It sits inside a geopolitical system where the US, Taiwan, South Korea, and Japan are all actively trying to preserve segmentation of expertise. The more portable that expertise becomes, the harder that segmentation is to maintain. And there's another layer people usually skip. Even if you successfully import engineers at scale, you don't automatically import the ecosystem they rely on. Tool vendors, material science feedback loops, defect analysis cultures, supplier trust networks. Those are geographically distributed for a reason. They evolved around decades of co-location. So the question that keeps coming up for me is this: can you actually accelerate a semiconductor ecosystem by buying individual nodes of expertise, or do you just create expensive islands of knowledge that don't immediately connect? There's also an uncomfortable asymmetry here. Western commentary tends to frame this as a talent raid, but inside China's industrial policy thinking, it looks more like compressing time. Not innovating faster in a linear sense, but skipping learning phases by importing lived experience. That distinction matters, because if it works, even partially, it doesn't just shift companies. It shifts how quickly entire fabrication ecosystems converge on parity. And that brings us back to that reported $800,000 figure. Whether it's exact or inflated, it functions as a marker. It tells you where the constraint is no longer capital, but time. And time, in semiconductor competition, is the only resource that doesn't scale. There's more to unpack here, especially around who actually accepts these offers and what restrictions follow them. But the real tension is already visible at this stage. There's a habit in Western commentary to treat China's semiconductor strategy as if it's mostly a procurement problem. Buy tools, hire talent, close gap. That model feels intuitive because it resembles how you'd scale a startup. But fabs don't behave like startups. They behave more like geological formations, slow to build, slow to stabilize, and brutally sensitive to small contamination in process knowledge. If you look at the historical reference point everyone quietly circles back to, it's Taiwan in the late 1990s and early 2000s. The rise of Taiwan's semiconductor manufacturing company wasn't just capital investment. It was the consolidation of process discipline under extreme repetition. The real asset wasn't any single engineer. It was the institutional memory of failure rates collapsing over thousands of production cycles. That's the thing relocation packages try to shortcut. Not invention, but repetition under pressure. Now, China already has domestic champions like SMIC, which has been steadily pushed upward in capability even under tightening US export controls. But SMIC's constraint isn't just machinery access. It's the compounding effect of missing generations of EUV-adjacent learning cycles that firms like TSMC accumulated with relatively uninterrupted tool access. So when a high compensation figure enters the picture, $600,000, $800,000, whatever the exact structure is, it's less about bidding for talent in the abstract. It's about trying to inject missing segments of that learning curve. But there's a subtle mechanical problem here that rarely gets discussed in policy debates. You can hire an engineer who knows how to stabilize yield on advanced nodes. What you cannot easily hire is the environment that tells them when their solution is about to break. In mature ecosystems, engineers don't just react to failures. They anticipate them because they've seen the same failure emerge in slightly different disguises across multiple fabs, suppliers, and equipment generations. That anticipatory layer is what actually drives competitiveness. Not raw problem-solving ability, but pattern recognition across industrial noise. And that's where relocation starts to show its limits. Let's say you bring in a handful, or even hundreds, of experienced engineers from Taiwan, South Korea, Japan, or the US. They enter a system where vendor feedback loops are still partially domestic, equipment supply chains are still under constraint, and cross-fab benchmarking is less transparent than in integrated global networks. What happens then is friction, not immediate transfer. I keep coming back to something an ex-Intel process engineer once described in a technical forum discussion, paraphrased, not quoted, about how moving fabs is less like moving a factory and more like retraining gravity. The tools are the same, the physics are the same, but the outcomes behave differently because every upstream assumption shifts slightly. That's the hidden cost in talent import strategies. And yet, there's a counter-argument that deserves respect. If even a small cluster of highly experienced engineers can reduce yield instability by a few percentage points in a cutting-edge node, the economic payoff is enormous. At scale, that difference translates into billions in wafer output efficiency. So we're not talking about marginal gains, we're talking about compounding industrial leverage, which is why the recruitment intensity feels rational, even if the execution is messy. But I still keep circling back to one unresolved tension. If expertise is portable, why does semiconductor dominance still cluster so tightly in a few geographic nodes instead of dispersing wherever capital flows? That question becomes more important as we move into the strategic consequences of this kind of hiring push. There's a point in every semiconductor cycle where policy stops looking like trade management and starts looking like controlled friction. Not full decoupling, not full integration, something in between that constantly raises the cost of being slightly behind. The US export control regime over advanced chips, especially the layered restrictions tightened since 2022 around high-end GPU interconnects and manufacturing tools tied to EUV-adjacent workflows, was never just about blocking sales. It was about slowing the accumulation curve. And that matters because China's response isn't symmetrical. When Beijing leans into talent import, whether through high compensation packages or targeted recruitment of overseas process engineers, it's essentially attacking the same variable from another direction, accelerating internal learning velocity rather than trying to restore full access to external inputs. But here's where the system gets complicated. Even if you successfully relocate expertise, semiconductor manufacturing is not a single knowledge domain. It's a stack of interdependent disciplines: plasma physics, chemical vapor deposition stability, lithography precision alignment, defect metrology interpretation, supplier calibration cycles. Each one evolves at a different pace, often in different countries. So what actually happens when you inject experienced engineers into a constrained ecosystem like China's current advanced node environment? You don't get instant parity, you get localized stabilization. For example, yield improvement in advanced nodes, say moving from unstable early-stage production toward commercially viable output, can often be nudged by experienced engineers who have already seen similar failure modes at companies like ASML-Linked or in Fabs integrated with Samsung Electronics. But those improvements tend to plateau if upstream constraints remain unresolved. That's the tension policymakers underestimate. Experience can compress uncertainty. It cannot eliminate structural bottlenecks. And China still faces structural bottlenecks in extreme ultraviolet lithography access, advanced photoresist supply chains, and certain high-end inspection tools. Even partial workarounds still introduce variability. In semiconductor manufacturing, variability is not just inefficiency, it is yield destruction at scale. Now, about the compensation numbers themselves, whether it's $600,000 or $800,000 packages being floated, there's an important analytical mistake people make when they see figures like this. They assume it reflects scarcity of engineers. It doesn't. It reflects scarcity of transferable engineers willing to relocate under geopolitical pressure. That's a much narrower bottleneck, and it changes the interpretation completely, because it suggests the constraint isn't global talent supply, it's trust, mobility risk, and long-term career irreversibility. A semiconductor process engineer isn't just changing jobs. In many cases, they are stepping into an ecosystem where future mobility may be constrained by sanctions regimes, export compliance rules, or informal blacklisting dynamics. That risk premium gets priced into compensation, which brings us to a quieter but more important question. If the global chip industry is fragmenting into parallel political blocs, does talent still behave like a global market at all? Or is it starting to behave like strategic capital? There's no clean answer yet, but early signals suggest something unsettling for the idea of open labor markets. Because the more geopolitics interferes, the less fluid expertise becomes, and the more each engineer effectively becomes embedded inside a national industrial system rather than a global professional network. That shift, if it continues, changes the entire logic of semiconductor competition. Not just who produces chips, but how knowledge itself moves, or stops moving. And that sets up the final layer of this discussion. What happens when states stop competing for factories and start competing for minds that cannot easily leave once they enter? There's a temptation to treat this entire story as a talent auction. One country offers more money, another tightens controls, engineers choose sides, and the system rebalances. Clean, almost market-like in its logic. But semiconductor ecosystems don't rebalance cleanly anymore. They accumulate political residue. And that's where this gets more interesting than the headline suggests. If you zoom out far enough, what Beijing is reportedly doing with high-value relocation packages isn't an isolated recruitment drive. It sits alongside a broader pattern: domestic subsidy programs, state-backed fabs, and coordinated efforts to reduce dependency on choke points controlled by firms like TSMC and equipment ecosystems anchored around companies like ASML-Linked. The hiring strategy only makes sense inside that larger architecture. On its own, it looks like overspending. Inside the system, it looks like time compression, trying to import decades of iterative failure learning in a few budget cycles. But I keep returning to a limitation that doesn't get solved by money. Even if you successfully attract experienced engineers, you still face the problem of integration depth. In semiconductors, expertise is not modular. It doesn't plug neatly into a new system like software libraries. It rewires workflows, supplier relationships, calibration habits, even how managers interpret acceptable defect rates. And those things resist acceleration. So my read is this: these relocation packages, if real and sustained, won't produce a dramatic leap in capability. They will produce something more subtle and arguably more important: A narrowing of the gap in specific bottlenecks, yield stabilization here, process debugging there. Small, compounding improvements that don't look like transformation until they suddenly do. But there's still a hard ceiling defined by external constraints, especially in the most advanced lithography and inspection layers. Talent can stretch that ceiling. It cannot remove it. Now the uncomfortable part. If this talent movement intensifies, it forces a response from other semiconductor powers, not just in export controls, but in retention strategies. We've already seen hints of this in tighter IP controls, longer notice periods, and more aggressive internal retention packages in firms across the US, Taiwan, and South Korea. The industry quietly starts behaving less like a global labor market and more like segmented strategic infrastructure. That shift is slow, almost invisible quarter to quarter. But over a decade, it changes where innovation clusters form. Here's my opinion on where this is headed. I don't think we're looking at a decisive brain drain moment that reshapes the industry overnight. That framing is too simple. What I see instead is a gradual hardening of expertise into blocks, where engineers still move, but movement carries political cost, and that cost shapes decisions as much as salary does. And that leads to a prediction I'm reasonably confident about. Within the next cycle of semiconductor expansion, compensation will matter less than permission structures. Not who pays more, but who is allowed, explicitly or implicitly, to move critical knowledge without triggering downstream consequences. One doubt I keep coming back to, whether China can sustain this kind of high-cost talent absorption long enough for it to meaningfully offset tool chain constraints, or whether diminishing returns kick in earlier than policymakers expect. That uncertainty is the real story here, because if diminishing returns arrive early, then these relocation packages become symbolic pressure valves rather than structural accelerators. If they arrive late, then we may be underestimating how quickly industrial learning curves can be compressed when money, urgency, and geopolitical isolation align. Either way, the semiconductor map doesn't stay static after this. It either quietly fragments into deeper silos, or it surprises everyone by reconverging faster than the current narrative allows for. And we're still early in that decision.